Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the organ printing course. So in the earlier lectures we have discussed about 3D bioprinting. What is 3D bioprinting? What are the different types of techniques available within this bioprinting? And then also we have discussed the first technology, that is inkjet printing technology. So in this lecture we'll discuss about the second type of bioprinting technology, that is extrusion based bioprinting. So in this technology basically this here we extrude a material through a syringe either using a pneumatic pressure or mechanical pressure in the form of filament, and then depositing or plotting that extruded material on the build platform as per the design. So the bioprinter here, it consists of a fluid dispensing system and also an automated robotic system controlled by the computer. Okay, so the fluid dispensing system that takes care of the extrusion of materials. So materials here is mostly it's either a polymer solution or a hydrogel or maybe a nanocomposite material or different other types of materials. A fluidic material mostly is being used, and that material is put into the fluid dispenser or inside the syringe, and then a pressure is being applied on top of the syringe so that the material comes out through the nozzle. So nozzle here, the dimension of the nozzle is in starting from 100 to several hundred micron, and then those material comes out. When you push that material through that nozzle, then it comes out as a filament. So that filament basically we are putting that on the build platform, and then by putting that filament as per our design, we basically can create several types of, or we can make or fabricate different types of structures. That is extrusion based bioprinting, right? Now the pressure that is applied on the extrusion based bioprinting, for extrusion based bioprinting on the syringe, can be of different types. Either it can be pressure time, that is the pressure can be changed with time, or it can be displacement time extrusion forces, right? Now printed here, that can move in all three directions like XYZ directions and deposit the filament on the build platform. In certain bioprinters, the printed can move in XY and the stage or the build platform can move in Z direction. In certain other types of bioprinter or extrusion based bioprinter, the printed can move in all XYZ direction. So any type of combinations can be possible, right? Then as I also already mentioned, the extrusion based mechanism of extrusion can be either, that can be the driven force for that can be either, it can be a pneumatic force, that is pressure driven, and here up, like this is the range up from 5 to 800 kPa of pressure, pneumatic pressure can be applied on that. With this kind of system, a bioinks of low to moderate viscous, like the range is 30 to 6 into 10 to the power 7 millipascal second viscous bioink can be used. And the second case of that is where it is a mechanical force driven, like displacement driven, where we are applying actually mechanical force for extruding the material. In this case, bioink is very high viscous bioink, like almost more than 6 into 10 to the 7 millipascal second viscous bioink can be extruded with this kind of bioink. So there are different types of extrusion based bioprinters available. Some works on this pneumatic force and some work on this mechanical force. Also the print head, if you see, the print head can be of different types. Either the print head can move in XY as I said, or and in that system the build platform move in Z. In certain case what happened, the printed can move in all XYZ direction. In certain other cases where when the printed can be stationary, it can move in only Z direction and the build platform move in XY direction. So any type of combinations can work, but the most common type is the where the printed moves in all three direction like XYZ direction and the build platform is stationary. Now here other thing is to remember here, the nozzle or not nozzle, the syringe or the cartridge, you can also the cartridge, the syringe can be put inside a temperature control jacket. So the temperature of the syringe can also be controlled. Either we can heat up the syringe or we can reduce that, or we can cool down the syringe. So any things can be possible. So temperature control syringe is also very much required to print certain type of biomaterials. So that is also there. Other thing is the stage temperature can also be controlled. So the stage, we can keep the stage at 37 degrees centigrade at room temperature or below temperature, depending on the required temperature. We can set the stage temperature accordingly, and we can print the structure. Now, as I also already mentioned, either the syringe. Suppose this is the syringe of the bioprinter, where it will be, or it is attached to the bioprinter, and then within the syringe we will fill the material. So this yellow color thing is, suppose this is the polymeric material fluid that we have filled within the syringe. Now we can, and this is the nozzle attached to this syringe. So if we push that material, it will come out through the nozzle in the form of filament, right? So here either we can apply the pressure by pneumatic pressure, by air driven, or by mechanical pressure, that is the piston, right? Or even also by the screw. Suppose the screw is attached. So based upon the threading, the screw will be rotated, and so that when the screw rotates, so it will push the material forward, and by this way also the material will come out through the syringe and as in the form of filament, and then basically this extruded filament will be deposited on the build platform or on stage, right? So this is the mechanism of extrusion based bioprinting. So this is the bioprinter from 3D bioplotter from Biotech. It has different components. I will describe in the next slide. But let us see a video from our lab how actually this extrusion based bioprinting is done. If you see here, this is the syringe or print head. Syringe is attached to the print head, and this is the nozzle that is attached to the syringe. Now when this is a pneumatic driven extruder. So when we apply pneumatic pressure, the material, here we are printing only gelatin solution. So the gelatin is loaded to the inside this syringe, and then a pneumatic pressure is applied. Here you can see the 0.2 bar, almost like 200 pf, 0.2 bar pressure is being applied on this thing, and then the material comes out in the form of filament that is being deposited on the print stage, right? Now here in Biotech 3D bioplotter, the different components are shown here. Like we have this extruder, two types of extruders are there. Here, this is a hot extruder. That means the temperature, the syringe is encased with a temperature control jacket. So here the temperature can go from room temperature to higher temperature. So it is good for any material where the printing needs to be done at higher temperature, right? For thermoplastic materials, where the temperature, the material should be liquefied before printing, so that the hot extruder can take care of that part. So now also similarly a cold extruder is here, where suppose we need to print the material at low temperature, like less than room temperature. So there also the temperature can come down. So here this is the printed. This printed move in XYZ all three direction, right? So this printed, so what will it will connect one extrude at a time. So if it is the function, then it will go and station here, and then another cold extruder will be connected, and that will come and that will be printed. So this is the stage here, print bed, and then when the actual printing is done, then we have different other things like the needle calibrator, so that we can calibrate the needle per station. All these things are there. It has different, it comes with different accessories, like it has stainless steel cartridges to be attached to this hot extruder. So the different types of cartridges are there, and different types of nozzles, nozzles are there. So we can, the nozzle diameter, different diameters of nozzles are available, so we can use different types of nozzles. This is like, it is how when it is connected to the printed. So this is the nozzle here, the nozzle that comes out of the thing, and then here we can, so when we apply pressure, the material comes out of this through this orifice, right? So this is the 3D bioprinter from Envision-Tech. These are the different components of an extrusion-based bioprinting system. So most of the bioprinter, like most of the extrusion-based bioprinter, they have similar components. Maybe the attachment, maybe the geometry a little bit different, but most of them have similar components. Again, depending upon the capabilities, like depending upon the functionalities, the different types of extrusion-based bioprinter systems are available. Like some are conventional extrusion-based bioprinter, like we have shown that, like here, this is a conventional extrusion-based bioprinter. It has, then there are certain bioprinters with high degree of motion possible, like where the printhead can move in, like suppose the printhead can move in an uneven surface, also the printhead can move, and it can basically print. Even suppose if the surface is uneven, suppose the surface is like some kind of thing, then also the printhead can move in this thing, also the print, so the nozzle can be rotated, and that can be printed. So this kind of, nowadays this kind of systems are available, and that is very good, because in certain cases we need to the structure, suppose the geometry is such that we cannot print like this. If we can directly approach, cannot approach like this, so we have to do the printhead or the nozzle can be bent, and then it can be printed. So that kind of possibilities are there now with high-end extrusion-based bioprinter. That is possible. Then certain type of bioprinter, like extrusion-based bioprinter, where they support bioplotting process. So that is a different process, where basically we can plot the materials as per our design. So that kind of capabilities are there. Then support some kind of bioprinters that support cell aggregates. So cell aggregates can also be printed. Some bioprinters, they can do that. So that basically what it does is basically go and pick cell aggregates, and then that can be printed at certain pre-designed locations. So that kind of possibilities also there. And then other bioprinter, where it's not only extrusion-based bioprinting, other kind of bioprinting modalities are also attached. So it's a kind of hybrid bioprinter, where it can work with both like extrusion-based bioprinting, also some other kind of bioprinting modalities can also be attached. So different types of capabilities are possible nowadays, and it is all required, because along with this course, when you discuss more about these things, I will discuss where exactly, like what are the limitations of current bioprinting technologies, and what is required to reach the next stage, where actually exactly like we can go for printing solid structures like kidney, liver, so this solid organs. So where those cannot be print now, those are not being printed basically because the technology has not reached that stage. So when we discuss that thing, that time I will talk about these things. So what kind of bioprinters are like required for in the future to tackle this kind of problems. Let's discuss some of the characteristics of this extrusion-based bioprinting. Like if you see here, like we have in the earlier sections, we have discussed about inkjet-based bioprinting. There we have discussed in detail about what is the possibility, what are the different characteristics of this. Now in this case, we'll see, if you talk about extrusion-based bioprinting or extrusion bioprinter, the most important characteristic of this is highly affordable. Like many people, like nowadays, these printers are not very expensive, so this is highly affordable. So anybody can use that, and these are not very the working principle are also very simple. So we need to so that many people can work, the researchers, they can also work on this technology. So it is highly affordable. It's highly versatile, because This it has the capability of printing different types of materials. You can use any type of materials. Either it can be solubilized form, it can be in the emulsion form, suspension form, it can be in suspension form. It can also, you can also use different composite materials, can also be used within this type of kind of things. Even we can use different cells, cell clusters, spheroids. All these different types of can be used as a bioink. So this is highly versatile. So we, and also we can print different types of stress structure, different types of structures, 3D geometry, whatever. We can create the geometry, and then basically we can fabricate that with this kind of bioprinters. The other important characteristic of this technology has the capability to fabricate complex and hollow constructs. If you see, printing a complex construct is very challenging, but with extrusion based bioprinting, that possibility is there, definitely there. So where we can definitely create a complex architecture, because the process is such that we can design, and then we can control how the printhead moves and how the material basically extrudes through the nozzle. We can control all this, and then we can print. Another thing, we can also use more than one nozzle at a time. So more than like 2 or 3 nozzles can be at a time, can be used simultaneously to fabricate complex constructs. Another thing, hollow construct can also be printed, because we can create the hollow structure within thing. So that is also very possible. So that's why the extrusion based bioprinting is one of the most commonly utilized technique in bioprinting field, especially. And this has been employed for printing different types of tissue structures like living cells. Definitely different types of cells have been printed with this technology, and researchers have shown the possibility of printing, like now it is more than almost like 50 or 50 to 60 different types of cells have been printed. And the most amazing thing is the cells are very much alive after printing. So that is important thing or characteristics of this extrusion based bioprinting. So the different tissue constructs have been attempted, and there are proof of concepts available where printing of different types of tissue constructs, starting from skin to liver to cornea to muscle. Different types of tissue constructs have been produced or fabricated with this extrusion based bioprinting techniques. Organ modules, different organ models we have, that is organ models have been fabricated with this extrusion based bioprinting techniques. So that is also very much possible, and those models have been used for different applications. Now organ on a chip devices, that is another area where extrusion based bioprinting is coming in a big way, because nowadays the trend is to use in vitro models, tissue or organ models, for drug screening, toxicity screening, and also for different other applications. So where also extrusion based bioprinting has been used widely for developing this kind of devices. So these are the things that has been already been done with extrusion based bioprinting. Now, why extrusion based bioprinting is widely used? What is the advantage of doing that? Basically, as I already mentioned, some of these things I have already mentioned, but again, let me discuss a few more things, like because this technology has the capability to print high cell density bioink, right? Because if you see in our tissue, so in some of the tissue, the cell density is very high, like it can be of order of 10 to the 7 or 10 to the 8, like, so it's like 10 million or 100 million cells per ml, right? In that much dense. So that much dense cell density can be printed within this bioprinting. So that's a huge advantage of this technology, because there in that case, then we are reaching somewhere very close to the native cell density, and that is required for bioprinting of this kind of structure. Where if we are to suppose we are trying to mimic that kind of tissue structure, then that is very much required. So then we can get the function of that particular tissue. So that's why printing high cell density bioink is definitely is a very big advantage. Other thing is the high viscous bioink for certain applications, because we are trying to print something like suppose we are trying to print centimeters size of few centimeters size of tissue, right? So there, suppose the requirement is that that should be the structure should be self-sustainable, it should be stable. So to do that, certain cases we need to print high viscous binding with high viscous binding, so that the stability of the structure is retained and the structure doesn't collapse. It is self-sustaining. So that kind of thing. So high density. So this bioprinting technology has the capability to print high viscous binding. So that is another big advantage. Then the other thing is, if you see in our tissue, then the most of the tissue is not a single cell. It's composed of multiple cell types, right? And those cells are arranged in a particular order. There is a hierarchy. There is a different positioning or locations of cells. So if we can create, or if we would like to create that kind of complex 3D construct, then extrusion by bioprinting is a big advantage for in that case also, because this technology has the capability to print complex 3D construct with multiple cell types and using different types of materials, right? Then the next advantage is the scalability. Now, printing small structure is possible with different other technologies, but if suppose we were trying to reach somewhere, say, centimeter scales of tissue, where suppose we are interested to print a big tissue with all the inherent complexity, all different types of cells, suppose inherent vasculature. So the scalability is a big factor. So this technology has got that thing right, because with this extrusion bioprinting, we can print this tissue of different cells, and we can also keep on doing that thing with this extrusion based bioprinting. So that's a very big advantage of this. Other thing is the commercial affordability. Now extrusion based bioprinters are very much affordable. There are many vendors or many bioprinting companies are available who provide this kind of extrusion bioprinting. Those are very much affordable. So commercial affordability is another advantage of this technology. So these are a few of some advantages of this extrusion based bioprinting technologies. Now let's talk about the evolution of this extrusion based bioprinting. If you see historically, extrusion based bioprinting technology evolved from that is called fused filament fabrication technology. That is where the thermoplastic polymers are used for printing structures. How they are being printed? These thermoplastic polymers are put inside through a print head. Those thermoplastic polymers are first heated to a certain temperature when they liquefy, and when they are liquefied, then they are being pushed through the nozzle. Then this molten thermoplastic polymer or liquefied thermoplastic polymer that comes out of the nozzle, then basically we plot them, those filaments, we plot them into and then we produce the 3D structures. Now this extrusion based bioprinting has evolved from that fused filament fabrication technology, but here we don't have this simple only printed, but we have a syringe where here we load the material, and then if required we heat up that material. So that material is liquefied, then we apply pressure, so the material comes out of the nozzle as a filament, and then we can print them into a 3D structure. We can also load hydrogel polymer solution inside the same syringe, and then but we can control the temperature. So suppose we need not to heat them, we can, suppose if we want to cool them, we can control the temperature, we can reduce the temperature of this print head, and then the material can come out this thing. So if you see historically, at the very first, like in past, this extrusion based bioprinting was mostly used for printing only biomaterials, where no cells are encapsulated or loaded inside the material. Only 3D printing of polymers are mostly used. So like polymers like PCl, PLGA, PLA, all these things are either they can be in a dissolved state, like these polymers can be solubilized in a respective solvent, or these polymers can also be heated up to liquefy, and then that can be plotted. So these things are possible, and then after printing, the cell seeding was done on this kind of structures. But here the disadvantage of this, we can produce very nice or complex structures with this only printing only polymers. But the thing is that later on we need to seed cells on top of this. Now the cell seeding is in certain cases cell seeding is challenging, because when the cells are seeded on these things, the cell attachment is not even, they attach to a certain area, not the whole thing. So the uniform cells attachment is another big problem. The other challenge was, we cannot achieve the cell density like the tissue, because that much cells attachment is very challenging. So then the researchers have moved on from there, and then in recent past, like they have been printing with bio-inert material like alginate or some other material, where these materials are loaded inside the syringe, where the cell, in certain cases cells are also encapsulated within this material, and those are being extruded through the syringe, and then those are being plotted or printed on the stage, and different types of structures are made. But the disadvantage, this encapsulated cells, that in certain cases it was found, then there is a reduced cell viability, also the reduced functionality of the cells, because these materials are mostly bio-inert materials. These don't support cell attachment as such. So that is also the problem. Now the recent trend, what happens, the bioactive materials are mostly used for printing of 3D structures, and either cells are encapsulated within this bioactive materials. Like recently, the cell instructive hydrogels are mostly used for preparing 3D structures, because so that we can provide the necessary cues for, or biological cues for, functional tissue fabrication. So the cell function can be fully established, because now with extrusion bioprinting, the current trend is to mimic the tissue structure. So there is not only the structure, mimicking structure, also the mimicking function of that particular tissue. So that's why the biomaterial or the bioink is very important, and nowadays the trend is to print with bioactive materials. So that's the current trend. When you talk about different bioprinting technology, then process parameters are very important. So we need to control we need to modulate the process parameters, so that we can control we can optimize the bioprinting process to print a suitable structure. Like the viscosity of the materials is very important for extrusion based bioprinting, because the viscosity is the material, that how the material will extrude through the nozzle, that will depend upon the viscosity. Accordingly, the pressure will be correspond to the viscosity of the material. But for extrusion based bioprinting, the requirement is mostly the material that has shear thinning property. So the rheological, the viscosity of the material, it has a shear thinning property. That means if we apply pressure, then the viscosity of the material comes down, or that is thinning of the material upon applying pressure. So shear. So that shear thinning material is mostly used for extrusion based bioprinting. So viscosity of the material is a very important parameter, and we need to control, or we need to modulate the viscosity, so that the extrusion of the material, or in a way bioprinting of the structure, can be controlled or modulated. Right? The next parameter is the nozzle diameter. Now nozzle diameter is very important, because this nozzle diameter basically dictates the resolution of printing. If suppose your nozzle diameter is very good, nozzle diameter is suppose very fine, then the extruded filament also will be very, very nice, very fine. So the diameter of the nozzle directly correspond to the extruded filament diameter. Right? So the nozzle, that's why nozzle diameter. But the one thing is, if we use nozzle, very fine nozzle, then what will happen? The material, we have to apply a lot of pressure for extruding the material or extruding cells. That can cause sometimes that can cause cell damage, because of this shear force that is acting on the cells. So that due to the shear stress, that the cell can get damaged. So nozzle diameter we have to choose accordingly. So if we choose low nozzle, the very fine nozzle diameter, the resolution will be very good, but that can cause damage to the cells. But if we suppose if we select nozzle diameter of very high nozzle diameter with a wide diameter, then the resolution will be bad, resolution will be not that great, but that will be good for cell viability. So we have to somewhere we have to work with this thing, and then we can accordingly we can select the nozzle diameter. Nozzle type is another thing. Suppose we can use either straight nozzles or we can use either tapered nozzles. It has been found that when we use a tapered nozzle, then the shear force or the shear stress generated only at the tip of the nozzle. In case of straight nozzle, the shear stress generated across the wall of the nozzle. So we have to also accordingly we can choose different types of nozzle based upon our requirement. Other thing is the other process parameters, the pneumatic pressure or mechanical force. What is the how much applying pressure being applied? That is also a process parameter, and that is depending upon the viscosity and the nozzle diameter. We need to control the pressure accordingly. The another parameter is the extrusion rate, the rate at which the material is coming out from the nozzle. That is also a important process parameters. The extrusion rate can be very high also, but if the extrusion rate is very high, again the same thing. Again, it can may cause generate a lot of shear stress, and then that can be detrimental for the encapsulated cells. If the extrusion rate is very slow, then it can also the time required for printed structure will go high. So accordingly, we need to also control the extrusion rate. Print speed is another parameter, the rate at which the print head moves during printing. That is the print speed. So the print speed it should be in accordance with the extrusion rate. Suppose in our case extrusion rate is we set a certain extrusion rate, the print speed should be such that the material comes out that much so that we are able to make a very good line or structure. If suppose the extrusion rate is low, print speed is more, then the material will not come out uniformly, or we cannot print a very good structure. If the extrusion rate is very high and print speed is low, then what will happen? The more material will come out, but we will not be able to make again good structure. So we have to control both these things in accordance with each other. The other requirement is the gelatin kinetics, because for extrusion based bioprinting, one important requirement is whatever the material is coming out, it should have fluidic. It is fluidic nature when it is coming out of the nozzle. But as soon as it come out, it should be able to solidify. So this solidification process is very important, or gelatin process of that fluidic bioink is very important for extrusion bioprinter. So that can be achieved by different ways, like either it can be some kind of chemical cross-linking, it can be photo cross-linking, or it can be also ionic interaction. So any types of cross-linking mechanism can be possible for gelatin kinetics. We have a separate in the later on in some lectures. I will discuss more about this, how this gelatin kinetics process can be controlled. What are the different types of gelatin possible for this bioprinting? We'll discuss in detail about this thing. So thank you all for listening. The rest of the thing for this extrusion bioprinting we'll discuss in the next lecture. Thank you.